All right, today we're going to make a very, very big step. We have studied our basic vector space, V. We've studied our dual space. We've studied all of our tensor product spaces that we're interested in. And we've got that down. We understand that these are maps that take vectors to the real numbers. We understand that these are maps that take Cartesian products of vectors and covectors to the real numbers. We understand that these are maps that take covectors to the real number. Everything is sort of a map. And we've got all that down. We know how to write arbitrary vectors. We know how to write arbitrary covectors. We know how to change bases to a different basis. And we know how to, this should be a hat, I should write a little slower. And we know how to write these arbitrary tensors, alpha, beta, gamma, dot, 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 delta, epsilon, eta, dot, 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 right? V, tensor product, V, tensor product, dot, 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 V star, tensor product, V star, dot, 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 anything like that. And so we've made all this. Now understand, we've made all this based on nothing more than our original vector product space, which was a real vector product space of dimension 4 with some basis vector. Starting from there, everything else automatically invented itself just through logic alone. And this is a critical point. I mean, we've really just kind of adding nothing, adding no new elements except for this. This is the only thing we created. Everything else sort of follows logically. And we've been very strict about not adding anything new. Well, this is the lecture where we actually add something new. So just focusing on the vector space, I'm now going to look for a function, a single function. And that function takes two variables, two slots, and in each slot is going to go a vector from the vector space. And this function is going to return a real number. This function is a new object. There are many possible functions, but the intent of this function is it takes a vector v and a vector w, which are arbitrary elements of the vector space v, and it gives you a real number a. And that function is going to be added to the collection. So if we did our little box, we would say v is a real vector space of dimension 4 with a basis. Oh, and it also has this function that takes two vectors and returns a real number. And, and so we now are going to talk about what kind of function we actually want. This function has to satisfy some certain key properties. The first key property is that when this function acts on a vector, two vectors, it gives you a real number. We've already called that out. The second property is if you take a constant and a scalar multiple of a vector and you throw it in the machine, that this will just equal that scalar that's multiplied in there and return to you the function operating on the two vectors. So that is, it's linear. It's linear in, well, or it's homogeneous or linear. There's a couple different words for this, but it's basically linear in this scalar lambda. This is lambda as an element of the real numbers. And this is true for both of the terms. Okay? Then the other thing is that the sum of two vectors operating on a third vector simply equals the sum of the function. This is another notion of linearity, right? This combined with these two make sure that everything is linear. Okay? And then we also want this to be symmetric. It doesn't now, there are this is what we want. For general relativity and the way we're working on this, we want it to be symmetric. However, in full mathematical generality, this is not required, right? This is not, doesn't have to be that way. You can have anti-symmetric functions that serve the same purpose. And there's another thing that tends to show up when we have this conversation, which is this function operating on the vector itself. Very frequently you'll see references that define all this stuff, and this thing has to be greater than 0 or equal to 0. And if it's equal to 0, then v must equal 0. In other words, if f of v equals 0, it's only true, I guess you're right, if and only if v equals 0. These two properties we are not using. We are not invoking those two properties. This function is called an inner product. And frequently, inner products are defined with this property in place. And frequently, it's also defined without this being in place. It depends on where you're going to go. But for general relativity, this is definitely in place, and this is definitely not in place. And this is also called the metric. The metric is another way of choosing this, of calling this function. So a vector space that has a metric is called an inner product space. Or it's called a metric space, with the caveat that some books define metric spaces with these other properties, with these two properties in particular, but we do not. We do not. But understand, this is something we have added. We're not talking about every possible function anymore. We're not saying, oh, take every possible function and that's a metric. We're saying, no, no, no. We are making, we have a vector space. We have a vector space, and we are adding a single function that we like, that we're picking for whatever reason. We're going to pick a single function, and we're going to drop it in the set of core things that make up the metric space, including its addition property and its scalar multiplication property. It will also have this special function that's called the metric function, or the inner product. And then our metric space, our vector space gets promoted. It's a promotion because it's got something else. And mathematicians love that word. Oh, we're going to promote this to an inner product space. But that's what we've done. We've promoted it by giving it this special function. And there's a few different notations we could use for this function. The one I've used already is literally a function, right, where you say VW and you get a real number. Another way of doing it is mimicking an ordered pair. You use parentheses, right? V, comma, W equals A. So you just drop the F. This can be confused with some ordered pairs, but really we don't use ordered pairs that much. The tensor mappings that we did before used ordered pairs, but we won't use that notation anymore. So this won't be too ambiguous, and actually this is the one we're going to use. In quantum mechanics, this is done this way. You use the bracket notation to describe your inner product. And there's a lot of good reasons for doing it in quantum mechanics. However, it's best used with complex vector spaces. And there's a reason for that. But so we're not going to use this one because although it does really say the same thing and we could use it, we're not going to. The other one is to use the elementary physics notation, V dot W equals A. The dot product of your elementary physics vectors is in fact an inner product. It's an inner product. It satisfies these rules, but it also has this rule, by the way, because you've never seen V dot V be less than 0, right? So, because of that, because it evokes that recollection of elementary physics where this greater than 0 rule is in effect, we won't use it. That greater than 0 rule is, by the way, is called positive definite. If this applies, your metric is positive definite. And if it's not, it's indefinite. And if it is indefinite, then your metric space, this space here, is called a, well, if it is positive, if it is, let's go the other way. If it is positive definite, you have a Riemannian metric space, a Riemannian metric space. If it's indefinite, you have a pseudo-Riemannian metric space. General relativity uses pseudo-Riemannian metric spaces. So we're not going to use this form, we're not going to use this form, not going to use this form. We'll use this form to describe our metric. All right, so now that we've got the idea of what we're looking for, how do we define it? How do we define a metric? If we're going to pick functions, we've got to figure out how to actually build a metric. Because remember, we have to be able to come up with a rule that we can apply with any vectors, any two vectors in V. This rule has to work. So I'm going to erase everything here. And back to the drawing board. I always like to start with our real vector space, 4 dimensions, E mu, and now it's actually got this function in here, this inner product. So the way we define it, of course, is let's have a look at, well, what if I use two arbitrary vectors, A mu, E mu, A, oops, I don't want to use A, right? B nu, how about B nu, E nu, like that. Now notice, this is not a mapping, right? This symbol is different, and a mapping would require a dual vector and a vector. But here we have two vectors, and that's why, and this machine lives entirely in the vector product space. This function is a map. All functions are maps, but this is not a dual space mapping. This is an inner product mapping. It's different. We're singling out a special map that only applies by showing these brackets. Now, you may have other vector spaces in your world, and each time you use parentheses, it can only apply to the metric that is associated with the vector space associated with these vectors. Both of these vectors must come from V. If I had another vector space, W, which was 4-dimensional and real, and it had its own inner product, and it had its own basis vectors, say F mu, I cannot put a vector from W into the inner product from V. I cannot do that. W has its own inner product, and it would take its own two vectors and putting into its inner product. You can't do it. You can only use the inner product with vectors from the space to which it's assigned. All right, that's an important point, but it's almost kind of obvious at this point too, right? All right, so, working with this object here, what do we do next? Well, it's linear, right? So I go A mu, B nu. I take the constants out front right away, and I end up with E mu, E nu. So this is a real number because it is the inner product acting on two vectors, in this case basis vectors, and this is a real number multiplied by a real number. But the sums are in effect too, right? So you can think of this as A0, say, for example, B0, E0, E0, plus A0, B1, E0, E1, plus A0, B2, E0, E2, plus A0, B3, E0, E3, and then plus A1, B0, E1, E0, plus A1, B1, E1, E1, and I think I'll stop there until you finally end up with A3, B3, E3, E3. Okay? So any two vectors driven into our inner product function, this is the result. This is the result. Now, presumably, if we put two vectors in there, we know the components, so we can always figure out these leading coefficients. The problem is these things. And just as with dual space mappings, if we define each of these values, if we say the inner product of E0, E0 equals, and I tell you what that number is, and I tell you what that number is, and I tell you what that number is, then we've got everything we need to calculate the real number that it's involved. So just like before, if you know what the inner product does on the basis vectors and all combinations of the basis vectors, then you know how it operates on any vector in the vector space that's expressed in that basis. So in order to define an inner product, I just need to say, okay, E0, E0. Let's say that equals, well, I'm going to say that equals 3. And then I say, well, E0, E2. Well, I guess I should do it E0, E1. And that equals pi over 2. And I'm being whimsical here, so E0, E2 equals negative 3.5. And E0, E3 equals, say, e to the 3.33 power. And then I just do this all the way until I get E3, E3 equals, and then I put in some number there, like say 10. And so this activity is me defining an inner product. Because once I've got that, then any two vectors I put in, I can do this calculation. And each of these I've defined using my choice of inner product, and we get an answer. You'll notice that I've chosen a negative number here, right? Which means this term, this E0, E2 term, right? This term here, E0, E2, this number could be negative. This term could definitely be negative. I mean, if, say, these were positive. I guess any of these terms could be negative depending on the coefficients. But the point is, if it's negative, if any term is negative and big enough, right? And if any term is negative and big enough, it will drive everything to less than 0 because, and that's fine because it's a pseudo-Riemannian inner product space, and everything can be less than 0. So, and in particular, in special relativity, the rule goes like this: E0, E0 equals negative 1, E0, E1 equals 1, E0, E2 equals 1, and E0, E3 equals 1. That's very common in special relativity if everything is in the right coordinate system and the right basis, but all the others are 0. So the way we write that is E mu E nu equals eta mu nu, where eta is basically eta, this is eta 0, 0, eta, I'm sorry, this should be E0, E0 equals negative 1, E2, E2 equals 1, E1, E1 equals 1, and E3, E3 equals 1. It's diagonal, right? It's diagonal. So this should be eta equals eta 2, 2 equals eta 1, 1 equals eta 3, 3. And eta is called the Minkowski metric. And it's just the diagonal, so it's just a metric with this diagonal. And even this is not consistently defined in textbooks and in research papers. Sometimes it's reversed, where this is plus and these three are minus, right? And you'll see that almost an even split, with a little bit of a tendency to, for general relativity to have the mostly minus convention, and a little bit for the particle physicists to have the plus convention, I think. I'm pretty sure that's right. I might have that the other way around. But either way, particle physicists and general relativity tend to favor one over the other a little bit, I've noticed in the books I read and I've heard from people say, explaining it to me, but that's not totally clear where or how much. But regardless, that's only special relativity, right? In general relativity, these numbers can be very complicated, and we'll talk about, of course, that's where we're headed. We're headed to talking about it. Now, I will say, I'll give you a little foreshadowing. The whole goal of general relativity, I've already pointed out that we can pick. We can pick our inner product, right? And we do it by look at this whimsical arbitrary thing I've done. The trick in general relativity is not to pick it arbitrarily. Nature has a way of picking the inner product spaces that matter in general relativity. And the goal is to figure out what inner products nature actually picked. So that defines the concept of the inner product space. And you may be thinking, well, heck, this mapping looks awful lot like a dual space mapping from this tensor product space, V star, V star, which is T1, 1, the tensor product space, one dual space and one dual space. I'm sorry, not T1, 1. It's T0, 2. It looks like, isn't there a tensor in T0, 2 that looks like G mu nu E mu E nu? That's a tensor. That's a mapping that lives in this tensor product space that should take two vectors and give you a real number, right? This thing, G mu nu E mu E nu, that thing maps two vectors and gives you a real number, right? Well, that's exactly what this does, right? Using the notation we had before with maybe the F there if I wanted it. This is a mapping that takes two vectors and gives you a real number. What's the difference? What's the difference? Can I find a map in this tensor product space, this 0,2 tensor product space that mimics the inner product? And the answer is, of course, yes. And this thing is called the metric tensor. And we'll talk more about that next time.